taking the samples to the lab. Even if some of them succeed taking the samples to the labs, they take days to weeks. And before the result of the diagnosis would be out, a lot of damage would have been done in their farms. Then there is also uncontrolled outbreak. And this leads to blindly or shadowboxingly using antibiotics desperately in their farms to secure their investment in their farms. And everything culminates into antimicrobial resistance, causing more mayhem, both to poultry production as well as the public health. Next slide, please. So on this slide, you will see the actual breakdown of the factors that contribute to this ever-increasing antimicrobial resistance and failure in poultry production. We have biological barriers. These biological barriers, some of them, I never knew about them until we started this research. Uh, Things as simple as chlorine, having residue of chlorine in water. Immediately you use it to prepare the vaccine. Also, fungi from feed. If the feed is stored in dampy area, aspergillus grows, and that is capable of rendering the vaccines to become inactive. And also antibiotics. Most of the feed that they use in feeding poultry beds, they will tell you it is medicated. It is not supposed to be medicated because the medication also works against the vaccine. Then we also have a fake drug. Fake drugs is epidemic in this part of the world. Most of the drugs are fake, and there is no way for you to check them, because once they pass through the regulatory agencies, they start counterfeiting whatever they like. Then the diagnostic chasm, because the tools are not there and the tools are far away in labs, and the personnel that are supposed to take care of the diagnosis are not even anywhere near the farms. So that also causes a lot of loss in poultry production. Then the last mile infrastructure. For instance, if a shop where they sell vaccines for poultry, it will be most of the time in the city. Then the farmer goes to the city, buys it. Those the 2 miles that he will travel to his farm, the vaccine will no longer be inside a cooling system. And the heat shock, because Africa here, the temperature is always very high, the heat shock will lead to the inactivation of the vaccine. Next slide, please. Thank you, Enrico. Sorry for stressing you.
No problem.
On the next slide here, we have by the numbers. By the numbers, the magnitude of the problem we are trying to solve is very high. In Nigeria, it is estimated to be death of 70 million birds annually. That of India, because the members of the team are basically from India and Nigeria. So we are focusing on the two countries and region. Pardon. The mortality rate is always 80%. Imagine where you stock 100 beds, and then you know at the back of your mind that you're losing 80% of your investment. It is heartbreaking. 80%. Then the economic value per bed, if it gets to maturity, currently in Nigeria, 15,000 naira. This the $10 figure is not right. 15,000 naira should be about okay. It's actually $10. Then the equation output we have in India is about 3.7 million US dollar, but in Nigeria is $1 billion per annum. That is the magnitude of the loss. Next slide, please. Thank you, Enrico. So during our brainstorming, we someone brought up the idea that if we are going to take care of this, it should be a kind of a holistic and systemic. So before then, we had gotten the five major prevalent diseases of poultry to include Newcastle disease, followed by coccidiosis, infectious brucell disease, infectious bronchitis, avian influenza. Then, after the consideration, we had to include a representative of the bacterial family, E. coli, and then Aspergillus for the fungi family. Then it is worthy of note that avian influenza, though is the most virulent, but it is not prevalent. It doesn't, the frequency of occurrence is always very low. Like in Nigeria, all my life, I think the only time it has happened is in 2007, but the damage was devastating. So we will approach it in a modular format. For now, we want to focus on Newcastle disease and coccidiosis using Frugal science tools. Next slide, please. Yeah, thank you. So our intention is to move from the chaotic and the perfect storm system to the path of resilience and sustainability, which is the Frugal science part. On the slide, you can see 80% mortality, then the last mile infrastructure gap. There is no cooling van. The person may even ride on his bike. The sun will be beating whatever container or bag he has put the vaccine, and then the temperature is always high. And also lack of knowledge on the part of using chlorinated water. The common practice here in Nigeria is that if you want to administer vaccine to your birds, you have to use the most acclaimed pure water. We call it pure water here in Nigeria. That is treated water, put in bottles or in sachet. But most of the time, there will still be traces of chlorine, and that will instantly deactivate the vaccine. So the Frugal science approach will make use of ultra-low cost field deployable diagnostic tools. In this case, we are looking at real-time lamp. We are looking at handy fuge or paper fuge. We are also looking at the full scope. Next slide, please. So the Frugal science paradigm shift will also be incorporated with frat pack validation. So along the line, we'll be checking the functional requirements, the design parameters, the analysis. We'll be making references to already existing, established, and successful tools. And we'll also be monitoring.
Oh, Kennedy, can you hear us? Yeah, you're back. Kennedy, we couldn't hear you for like 5 seconds. But
Yes, I'm back. Someone.
Yeah, you're back. You're back.
Yeah.
Yeah.
Next slide, please, Enrico. So the diagnostic strategies that we're going to deploy will be focusing on coccidiosis and Newcastle disease for now. So the parts for Newcastle disease, we'll use it as, we'll adapt it for other viral diseases because most of the diseases of poultry are viral diseases. Then also the one for coccidiosis, will adapt it for even other parasitic diseases, both in human. Next slide, please. So on the next slide, we are going to x-ray the current coccidiosis diagnosis. The diagnosis was developed very long time ago. I think it says 1920s and 1930. So it's a long time ago, and technology has moved. So we are doing our best. We are attempting to integrate new and better improved technologies for this diagnosis. As it were, it is always labor intensive. It requires sacrifice birds. So you wait for your birds to die, or you have to kill your birds before you are able to carry out these tests. But the method we are going to deploy now wouldn't require the death of any bird. We pick it from the poultry droppings. Next slide, please. So the next slide is the proposed diagnosis protocol. Our protocol involves McMaster's fecal flotation using basic salt or table salt, and using a spatula, then a container. Then next is the quantification. For the quantification, we'll use um, a mesh filter, but the mesh will not be more than 10 microns, the size of the mesh, because the size of the protozoa, the eggs, is between 15 to 30 micron. So that will be able to trap it. And other constituents of the dissolved of the protocol are also less than 15 microns. So we'll do visualization using the full scope in collaboration with a smartphone. Next slide, please, for details. So in the details, we'll use 400 grams of table salt and dissolve and then make it up to 1 liter of water. The properties of this flotation solution is that it has a specific gravity of 1.18 to 1.20. Then because of that gravity, it is able to separate the eggs of the parasite that is 1.05 to 1.1. Then at the bottom, you have the debris and bacteria, fungi, whatever is left will be down at the bottom because the specific gravity is always greater than 1.2. Then we incorporated this filtration method from the method used by Prof, the method they used at Ogun State for schistosomiasis.
Yes.
Yeah, I've talked with Williams. He said he can send me a shipment of the filtration mesh. So that's the method we're going to deploy. So the filtration mesh, like I explained before, will be 10 micron. The aperture will be 10 micron. Then 15 to 30 micron is the size of the eggs we're going to filter. Every other thing is smaller in size and will pass through. Then after the dissolution, we'll allow the container to settle. The settling will allow the debris to go down, then the eggs will come up, then we decant on or through the mesh so that the eggs only will be caught on the mesh, and then we'll transfer to the viewing slide and pass it to the full scoop. Next slide, please. Okay, thank you, Enrico. So on the next slide, we can see the representation of how the setup will be and then the possible outcome. The total estimated cost per test will be between 0.1 to 0.15 USD. Next slide, please. Okay. So Aditya will take it from here.
Thank you, Kennedy, for the presentation so far. I'll be taking
Then
this
Aditya,
presentation
you
ahead.
should think you maybe have around 3 more minutes or so. So you have to be a
Yeah,
little
yeah,
bit
yeah.
fast.
I'll
Don't
be quick.
ask lots of
I'll be really
questions.
quick. Yes,
Yeah.
I'll be really quick. Yes, yes. So
And
as
I
we've
mean,
already
it's
said,
fantastic to see between the two talks. There is a lot of
yes,
commonality between what happens
yes,
in humans and what happens in poultry. So it's
yes.
the same series of
So
technologies, which is fantastic.
yes. So as Kennedy has already explained us that we have chosen two main organisms to be diagnosed. One is parasites and the other is virus. So obviously, the advantages that we have with parasites is that parasites can be observed under a microscope and also be captured in a low micron filters. Now, on the other hand, we have viruses, which we all know cannot be observed under a microscope, cannot be trapped in filter papers and everything. So, what is the solution for detection of viruses? So, the current detection methods for viruses, as we all know, the golden standard for detection is the polymerase chain reaction. But what is the disadvantage of the polymerase chain reaction? Is the PCR, the thermocycling machine itself, right? If we are aiming at something point of care and low resource setting diagnostics, we cannot expect the labs to have a PCR machine, nor even a centrifuge or anything like that. What one method that has intrigued me for the past few years is the loop. Sorry, Andrew, can you have the next slide, please?
Yes.
Is the LAMP method, which we all already learned in one of our initial lectures about diagnostics and laboratory. So I have greatly taken inspiration from the diagnostic under a tree, the lecture, and I went ahead and also read a few papers that were present on the website for the same. So the entire process of LAMP, the entire process of virus diagnosis, it has three major steps. First is the sample collection and sample enrichment, because we obviously want the virus itself to be part of the reaction and not the other material that can actually interfere with the reaction and give us false positive results or no results at all. So what can be done for the sample collection and the sample enrichment part is that we'll be focusing on swabs and blood samples. Uh, the extraction process is what I read from one of the papers that has been researched upon in Dr. Manu's lab was a filter paper based extraction, where all we need is a Whatman #1 paper that can be introduced to the sample, which can be grounded. So the DNA will attach itself to this paper, to the fibers of the paper. After that, obviously, the paper either can be washed through an wash buffer or it can be directly used in the sample. Again, the other problem that we had was, including in India and Africa, storage is an issue. And all these reagents, as we all know, they require a particular temperature, a particular conditions to store. How can that be solved? Again, like we have seen in diagnostics under a tree, we can lyophilize them in tubes. All we have to do is we have to add the sample to the tubes and run the reaction. Now, the major advantage of LAMP is that it only requires a single temperature, which is around 65 to 67 degrees Celsius, unlike the PCR, which requires thermocycling. So that removes an entire huge chunk of the machinery that we don't need at all. All we need is a small thermal block, which can also be powered with a battery, which can give us the particular temperature that we need. Now comes the readout part, because obviously, how are we going to evaluate the results? The results can be either evaluated through colorimetric assays, but what I prefer is an LFS strip, a lateral flow assay, like the pregnancy case, or many other tests that we already have at home. LFS strip gives you a very simple readout based on a control and a positive line or a control. If a line appears on the LFS strip, we have the results, and we know that there is something in the that there's something detected. Enrico, can you please?
Yes.
Yes.
So Aditya, you have 1 more minute, otherwise we won't get time for questions.
Yes,
So
yes,
this
yes.
is something that we
This is
discussed. I
just
want to
this
get
is just the
Aditya.
same. This is just the same
Yes.
protocol. I'm sorry. I'll just take one more slide ahead. Enrico, yes. So these are just the functional requirements, the analysis, the risks of diagnostics that are currently present, and how we are going to solve it. We have already discussed upon it, so I'd like to just move ahead.
Yeah, let's do questions, because I think one thing that we'll do is
Yes,
list
yeah,
out.
I
Yeah.
agree. Yes, I agree. Okay.
Okay, yeah, you wanna unshare? So Kennedy, Aditya, everybody in the team, I wanna take a minute or so on questions, so you can unshare the slide.
Okay.
Yeah, it's much more fun to see everybody.
Right.
So kind of, I think the first thing I wanna start with is, Kennedy, Aditya, and everybody else on the team. I mean, 80% of a stock loss is absolutely crazy, because you can look at the costs that's lost, and that could be put in the system. So it's broken in many ways, because farmers are losing so much money. And how is it that it's okay? And I think the way you described it, Kennedy, seems like the pipeline that exists for the food pipeline is very different from how we treat diseases in humans. And I mean, seems like every level there is a quality reduction that's associated. So I wanted to
Very
know the
much.
antibiotics that are fed to the animals, are they the same grade as the ones that are fed? Are they made with the same purity? I mean, I used to know that there was a massive fake drug problem that has existed for some time, but there has been a lot of action that's been taken. But has that problem just found a new market in the animal world?
It has been there in the animal loop. It has been there. And it is the same grade of antibiotics for humans that are also used for the animals. For example, tetracycline. Tetracycline is always integrated in the growth boosters.
But what I meant to say was, is it the same manufacturing plant? Is it the same entity making drugs for humans and it's making drugs for animals?
The common practice here is that the farmers also buy from the same drugstores that humans get their drugs for.
I see.
That's the common practice here. Although they also have designated shops where they sell poultry boosters, the feed, and all that concerns poultry.
Yeah. Well, what I meant in this scenario is it could be that the regulatory restrictions around manufacturers for humans might be tighter as compared to the one for animals. And then that could cause all kinds of trouble, because at the end of the day, we are actually consuming, and it would be even more complicated AMR problems if the regulatory standards don't apply. And then I want to make a last comment and then move to the next presentation. I think for both the fecal sample side of the story, and then I wish, Kennedy, you had included some pictures from the Nigeria trip, but we'll do that another time. Also, on the swab side of the story, rather than testing individual birds, can you look at something in the sewage or something else that's collective? Because, I mean, effort per bird could be much, much higher, because every farmer could have a massive amount of birds. I mean, the amount of chicken that is consumed in the world per bird, and if either they are symptomatic or switching to the sewage, which is really what has changed dramatically how we are monitoring diseases right now. So is there a pipeline to shift away from a single bird and a waste line that exists that is collective?
What we had in mind is the ideal approach should be sampling at random.
I see.
Yeah, sampling at random.
I see. But then you should do some numbers
That's a
before
great
you submit the
thought.
next report. Try doing some numbers for what changes if you are sampling every bird, when you're sampling kind of waste, which is also complicated because then you need a more sensitive test, or this methodology, which is statistics oriented, which is sampling at random. Because I think it's valuable to understand the cost numbers that we know very well about microscopy and lab. For them to apply in the animal world, you might need some statistics ideas to say for a farm of 1,000 birds, if I did 10 birds, would that be meaningful?
All
So
right, Prof.
just play with those numbers based on the R naught of how the infection spreads. Okay, we're
all
gonna
right,
run out
we'll
of
put that
time.
into perspective. Thank you.
So I'll catch you guys soon. Let's switch to the next talk.